Good morning, all. In our last class, we saw ordinary differential equations. In that, we saw linear differential equation with the constant coefficient. In today's class, we are going to see linear differential equation with the variable coefficient. In constant coefficient, we usually show complementary function and particular integral. First of all, we will see the method of variation of parameters. See the PDF, and the general equation of the second order equation is d square y by dx square plus a1 dy by dx plus a2 y equal to x, where x is a function of small x. So complementary equation of equation 1 is, so complementary function equal to c1 f1 plus c2 f2, where c1 and c2 are constants and f1 and f2 are functions. Then we know the particular integral p f1 plus q f2. Now this is third equations. So we usually find complementary function and particular integral for method of variation of parameters. So complementary function formula is c1 f1 plus c2 f2, and particular integral formula is p f1 plus q f2. Here the value of p is minus integral f2x divided by f1 f2 dash minus f1 dash f2 into dx. Now this is fourth equation, and the value of q is integral f1x divided by f1 f2 dash minus f1 dash f2 into dx. Now this is fifth equation. We'll substitute this fourth and fifth equation in equation 3, so we get particular integral value. So in general, the complete solution is y equal to the value of complementary function plus particular integral. So here we know that the value of complementary function is c1 f1 plus c2 f2, and the value of particular integral is p f1 plus q f2. So usually in our question, using our question, we will find the value of p, q, f1, f2 and everything. Okay, let's see the example. So in this, solve d square y by dx square plus 4y equal to 4 tan 2x using method of variation of parameters. So write the given equation as it is. So we'll change as an auxiliary equation, m square plus 4 equal to 0. So the value of m equal to plus or minus 2i. So my complementary function will become c1 cos 2x plus c2 sin 2x, because my value is real and also in imaginary. So plus 2, and for imaginary plus 2 I am using cos, and for minus 2 I am using sin. So complementary function will become c1 cos 2x plus c2 sin 2x. Next we have to find the value of particular integral. We know that the value of particular integral is p f1 plus q f2. Here the value of f1 is cos 2x. See, in the complementary function we denoted cos 2x. So that is the value for f1, and the value of f2 is sin 2x. Next we have to find the value of f1 dash and f2 dash. It is nothing but just differentiate it. f1 dash is equal to minus 2 sin 2x. So f2 dash, while differentiating sin 2x, we will get 2 cos 2x. So we have found f1 f2 and also f1 dash f2 dash. Next we have to find the value for denominator. So the denominator value is f1 f2 dash minus f2 f1 dash. So the value of f1 is 2 cos 2x and f2 dash is cos 2x minus, so the value of f2 is sin 2x and the value of f1 dash is minus 2 sin 2x. Just substitute in this equation, then simplify it. So take 2 common outside, so we get in first term cos square 2x. Next minus into minus will become plus, sin 2x into sin 2x will become sin square 2x. We already took this 2 as a common outside. So we know that the value of cos square x plus sin square x value is 1. So we noting cos square 2x plus sin square 2x is equal to 1. So our answer will become 2. Now we have to find the value of p and q, right, for the particular integral. So here I am denoting this as a formula, p equal minus integral f2x divided by f1 f2 dash minus f1 dash f2 into dx. So where x equal to 4 tan 2x, it is nothing but the right hand side of the given equation. So p equal to, I am substituting everything, p equal to minus integral, so the value of f2 is sin 2x and the value of capital X is 4 tan 2x into dx divided by, we already found the value for denominator, so the value is 2, write it down. So the denominator value is 2. We can cancel both 2 and 4, so divisible by 2. So in my numerator there is 1 2, so take it as common, minus 2 integral sin 2x into, so the value of tan 2x is sin 2x by cos 2x, write it, and into dx. So there is 2 sin 2x in our numerator, so it will become sin square 2x divided by cos 2x into dx. So there is minus 2 in common, minus 2 integral, so the value of sin square 2x, so sin square theta equal to 1 minus cos square theta, so the value for theta here is 2x, so 1 minus cos square 2x divided by cos 2x into dx. We know the formula for 1 by cos 2x, it is become integral secant 2x into dx minus the value of cos square theta and cos square theta will cancel each other, so there is only 1 cos 2x in the numerator, so my second term become integral cos 2x into dx. So there is a formula for the integral secant 2x dx is nothing but 1 by 2 log of secant 2x plus tan 2x minus sin, so integral of cos 2x dx, the value is sin 2x by 2. So there is 2 in the common and also there is a 2 in the denominator for both the terms, so cancel each other. So my rest of the term will become minus sin 2x plus log of secant 2x plus tan 2x. So I'm interchanging both the terms. There is a minus in outside and also minus in inside, so minus into minus will become plus sin 2x, next multiply minus inside, minus into plus minus log of secant 2x plus tan 2x. Here I find the value for p. Next we have to find the value of q and substitute in the particular integral equation. So what is the formula for q? We already know that q equal to integral f1x divided by f1 f2 dash minus f1 dash f2 into dx. So write the value for f1, it is nothing but cos 2x, and also we know that the value of capital X is 4 tan 2x divided by, and also we note the denominator value as 2, so write it down into dx. Cancel 2 and 4, it is divisible by 2, take 2 as a common, so integral cos 2x into the value of tan 2x will become sin 2x by cos 2x into dx. Cancel both cos 2x, so integral sin 2x into dx will remain, so the value of q is q equal to minus cos 2x, so the value of integral sin 2x is nothing but minus cos 2x. So here we found the value for p and also the value of q, so substitute in particular integral formula. So particular integral formula is nothing but p f1 plus q f2, so the value of p is sin 2x minus log of secant 2x plus tan 2x, the value of f1 is cos 2x. Next the value of f2 is sin 2x, so sin 2x, and the value of q is minus cos 2x. So I substitute everything in particular integral. Now I am going to simplify, just multiply this cos 2x inside the bracket, cos 2x into sin 2x, next minus cos 2x into log of secant 2x plus tan 2x minus cos 2x into sin 2x. My first term and third term will cancel each other because that is in plus term, this is in minus term, so first and third will cancel each other, so my second term will remain as it is, minus cos 2x into log of secant 2x plus tan 2x. So the complete solution is, we know the formula for complete solution, capital Y equal to complementary function plus particular integral. So what is the value for complementary function is c1 cos 2x plus c2 sin 2x, and also the value of particular integral is minus cos 2x into log of secant 2x plus tan 2x. Hence I find the value of complete solution using the method of variation of parameters. Next, we are going to see the linear differential equation with the variable coefficients. Here I am denoting a variable and also as a function. See the equation, an equation of the form x power n d power n y divided by dx power n plus alpha a1 x power n minus 1 into dn minus 1 into y divided by dx power n minus 1, etc. plus a and y equal to f of x. Mark this as first equation, where a1, a2, a3, etc. are constants, and f of x is a function of x, is called the linear differential equation with the variable coefficients. So the function usually denoting it as a f. So this is a variable coefficient. See, in equation 1 can be reduced to a linear differential equation with a constant coefficient by putting x equal to e power z or z equal to log x. So I am changing this variable coefficient into constant variation by using our last type method. See here, we already know that the value of x is e power z. Take log on both sides, so x become log x, and log e power z, it will become z. Now my first equation will become, see here, now dy by dx equal to, so both multiple and divided by dz on both sides, so dy by dz into dz by dx, which is nothing but 1 by x into dy by dz, because the value of dy by dz is nothing but 1 by x. So the value of dy by dx will become 1 by x into dy by dz. Take this x into the next side, so it will become multiplication, x into dy by dx equal to dy by dz. So I am denoting this d by dz on my right hand side as a capital D is dash. So my equation become x into dy by dx equal to d dash y. So in our question, if they ask the question to solve it in variable coefficient, we will use this formula for the first term. For the second term, I am going to proceed just like first we found dy by dx. Next we are going to find d square y by dx square. So keep d by dx and dy by dx is in bracket. We already know the value for dy by dx. See here, the value of dy by dx equal to 1 by x into dy by dz. Just substitute it and differentiate is, so using applying product rule. So my equation become minus 1 by x square into dy by dz plus 1 by x. So just multiple and divided by dz, both numerator and denominator, d by dz into dz by dx. Keep the bracket term as it is, dy by dz. Next, minus 1 by x square dy by dz plus 1 by x into, so just multiply d square y by dz square into, so the value in bracket dy by dz is nothing but 1 by x. Just substitute it. Next, the value of d square y by dx square is, so all the term as it is, just 1 by x into 1 by x will become 1 by x square. So take 1 by x square as common. So I am writing the second term as first and the first term as second, because I have minus term in my first term. So just exchange it. See here, 1 by x square d square y by dz square minus dy by dz. Take this x square into the right hand side, so it will become multiplication, x square into d square y by dx square equal to d square y by dz square minus dy by dz. So I am taking this into operational function as d dash square minus d dash into y, where d dash equal to d by dz. So this is the value for my x square value. Similarly, we can find the value of x cube, x power 4, x power 5, etc. So while substituting all this equation 1, 2, 3 and everything in equation 1, we get the value of differential equation with the constant coefficient. Then we can apply any one of the types to solve the equation. Let's see the example for this type. There is a question: solve x square into d square y by dx square plus x into dy by dx minus 9 into y equal to 10 plus 5 by x square. We already know that the value of okay, just in solution write given term as it is. So the value of d square by dx square is nothing but capital D. Take y as common outside. So my given equation will become x square into d square plus x into d minus y into y equal to 10 plus 5x square. So mark this as first equation. And also we know that the value of x is e power z or z equal to log x. And also we found in the linear differential equation with the variable coefficient, our equation 2 and 3, which is nothing but the value of x and the value of x square. So I'm using that 2 equation here because I have only 2 value in this x and x square. So x d dash is nothing but d dash, x square d square equal to d dash of d dash minus 1. So the value of d dash is d by dz. Mark this as second equation. Substitute this second equation in first equation. See, my x square d square will become d dash of d dash minus 1 and the value of x d become d dash minus 9 as it is into y equal to 10 plus 5 into, we know that the value of x is e power z. Here there is x square, so it will become e power 2z. I am bringing the denominator into numerator, so it will become reciprocal. So it become e power minus 2z. I am simplifying, just multiply this d dash inside the bracket, d dash square minus d dash, the remaining term as it is. So there is 2 d dash, one is in minus term and one is in plus term. Cancel both the terms. So minus d dash and plus d dash cancelled, and d dash square minus 9 into y equal to 10 plus 5 into e power minus 2z. See here, in there is constant 10, there is no e terms, so it will become e power 0z because there is no term, right? So I am changing this into auxiliary function because I have to find the value of particular integral and also complementary function for this equation. See, auxiliary equation. So m square minus 9 equal to 0. Bring 9 to the next side. So it will become plus 9. So m square equal to 9. So taking square on both sides, I get m equal to plus or minus c. So there are two values, plus 3 and also minus 3. So my complementary function will become a e power 3z plus b e power minus 3z. So I found the value of complementary function. Next we have to find the value of particular integral. So in the equation, keep y as it is and bring d dash square minus 9 to the next side. So it will become denominator 1 divided by d dash square minus 9 of 10 plus 5 into e power minus 2z. So just multiply this term into bracket, 1 by d dash square minus 9 into 10. So there is no exponential value, so I can take it as e power 0z plus 5 divided by d dash square minus 9 into e power minus 2z. So here the value of d dash is nothing but 0 for the first term and the value of d dash for the second term is minus 2. So I am substituting here 1 divided by, so first term becomes 0 minus 9 into 10 plus 5 divided by, here the value of d dash is minus 2. See in the exponential, so there is a value minus 2. So write minus 2 for the d dash, minus 2 the whole square minus 9 into e power minus 2z. So there is a term minus 10 by 9 because there is minus in the denominator, so I take it as a numerator, minus 10 by 9 plus 5 divided by, so minus 2 the whole square minus 2, we get the value 4 minus 9 into e power minus 2z. So my term will become minus 10 by 9 plus 5 divided by minus 5 into e power minus 2z. Here I found the value of particular integral. Next we have to substitute this complementary function and particular integral value in complete functions. See here, my complete solution is y equal to complementary function plus particular integral. My complementary function value is a e power 3z plus b e power minus 3z, and also my value of particular integral is minus 10 by 9 minus e power minus 2z. So I already know that the value of az is log x, just substitute it. So a e power 3 log x plus b e power minus 3 log x minus 10 by 9 minus e power minus 2 log x, and also I know the value of e power z equal to x, so I am changing that exponential value as x. A x cube plus b x power, that is minus 3 in my power, so x power minus 3 minus 10 by 9 minus x square, because that is minus 2 in my exponential power. So my equation will become, complete solution will become a x power 3 plus b divided by x cube. So I am bringing that reciprocal to the denominator, it will become plus sign, minus 10 by 9, and also bringing this x power minus 2 as a reciprocal, I get minus 1 by x square. This is my complete solution. Here we found the value of differential equation with variable coefficients. We will discuss the next topic in our next video. Thank you.